Thanks everyone for joining us. We will now officially begin today's webcast. My name is Andy, and before we begin, I have a few housekeeping items to take care of. Today's webinar, Data Preprocessing for Machine Learning, is scheduled for 30 minutes, including time for question and answer. After we complete the presentation, we'll go straight into Q&A, so please submit questions as they occur to you via the Q&A box on your Zoom webinar console. Due to the number of attendees, the phone lines will remain muted throughout the presentation. We will make a recording of the webinar and the slides available following the webinar. Our presenter today is Vlad Kazanov. Vlad is a machine learning engineer at Augur.ai. He has 4 years experience in general machine learning and 3 years in deep learning. Prior to starting at Augur over a year ago, Vlad worked as a data scientist for a number of European and American companies. Vlad, when you're ready, go ahead and take over, share your screen, and start the presentation.
Thanks, Andy. Hi, everyone. Let me know if everyone can see my screen well. So today we will talk about data preprocessing for machine learning. Okay, so at first I wanna tell some words about the motivation of data preprocessing. Besides one that Andy told already, that a lot of data spent by data scientists are related to data preprocessing. And like one other motivation is the difference between the data the machine learning algorithms works with and the data real users deal with. So as you can see on the left, the machine learning algorithms require some features which all should be numeric. In general, the name of the features doesn't affect on anything, and it's just kind of a black box algorithm which knows nothing about the data, but the algorithm only knows that it has some metrics with numeric values and tries to predict something. While in real use case, we have some structured data with some different kind of features and some like complexities like missing values, some categorical values which should be encoded somehow into numbers, and so on. And one other thing is data preprocessing usually can improve the accuracy of the final model because we can extract some information from the features which might be useful to predict the target feature. So moving on. In Augur, we pursue the following goals while creating the data preprocessing pipeline. So the first thing is make the dataset which can be fed to any machine learning algorithm. This is needed because Augur uses optimization over a bunch of machine learning algorithms, and despite some algorithms can work with categorical data natively, most of the algorithms can't do this, and we need to make the data in a unified format so we can optimize over all machine learning algorithms in our search space. Another goal is to extract maximum information from the data, because machine learning algorithms can capture some dependencies from the data, which is not trivial and can be seen by the human eye, for instance. And also, the more information we have, the better prediction should be. One other thing is actually training time. It usually depends on the dataset size mostly, and partially on hyperparameters. And it's important to make the dataset as small as possible without losing much information, because losing information will lead to poor performance. However, the huge model size can lead to enormous training time, which lead to bad hyperparameters with limited optimization time, or it will require enormous amount of time to find appropriate hyperparameters. And the final goal is to make as much as possible in a fully automatic way, because our machine learning platform tries to automate as much as possible routine work for the real user. So here is the tab from Augur, where you can see some options related to data preprocessing pipeline, and in further slides I will elaborate on them. You can see this tab on options while clicking on options button near to the run button, and expand this by clicking on advanced. And here are the options, preprocessor options. So at first, it's reasonable to remove all non-observable values. And there are three ways to do this. One is to drop this kind of observations. Another one is to drop the feature. And the last one is try to impute the data. So we drop observations or features only in case they have not much, they contain not much information. So there are two options in Augur preprocessor. Maximum amount of missing allowed, which states for dropping the features. And another one is the maximum amount of rows with not available values. So this there are default parameters for these options. However, user can change them for her preferences. So this parameter states for dropping features or observations. Otherwise, we try to impute the missing values with the taking an average over the feature and replacing with that value. So for instance, in this particular case, we will average over all non-missing values in H column and replace every none with that value. And for categorical values, we can't calculate average. We leave none as is. And in further slides, I will show how to preprocess them. So moving on, the date and time features. This process is more known as feature extraction or feature engineering, while we have some like feature in not good format, like the date, for instance, and machine learning algorithm wants sorry, to have some like derived features from this column. So we derive something like month, day, week, day, year, day, some absolute time, hour, minute, and so on. And as you can see here, for an hour, there are all values equals to 0 because hour is missing from the initial column. And this will be also, this is not an issue, and this will be handled further. One note is that some features are impossible to extract in an automatic way, such as holidays, or for instance, Black Friday, some other dates which are specific to for which we need some domain knowledge about the data. So in order to use them, it is suggested to add such features by user manually into the data. For instance, add some column with binary values like is holiday or not, or something like that. So moving on, categorical features is another example of feature engineering. So, for instance, consider an example where we have a feature called browser, and we need to encode it into appropriate format for machine learning algorithms. And here we use one-hot encoding, which is a natural way to encode such features. Imagine that in our dataset, the most popular browsers are Firefox and Chrome, and all other browsers takes like negligible amount of information. So in order to not produce too much columns, we bucket together all like less popular categories into one category. For instance, in this particular example, we bucket Opera and Edge browser into one category and called it other. So the final encoding will have this form, and recalling the not available values, we encode them as non-category, which is a natural way to encode the missing values for categorical features. And in Augur, you can set the maximum amount of categorical columns. By default, it's set to 50, but you can change it. For this particular example, it should be set to 2 in order to get something like this. Moving on, so feature elimination. Here we come to the part where we not expand the data set, but reduce its size in order to save computation time and leave more time for optimization of hyperparameters. So remembering an hour variable from previous example, we can use variance-based feature elimination for all columns. And for instance, for this column, the variance will be exactly 0. So this column will be eliminated from the data set and without losing information, because actually each value is 0, and this can't give us can't help us with predicting the target. And here is the option in Augur called variance threshold. It's the minimum variance value which should be in column in order to preserve it after this preprocessor. All columns with variance less than this value will be eliminated. So here are another example of dataset reduction. We use principal component analysis. It's also quite powerful tool, and it mostly works on the sparse data. So we treat some feature as sparse if it has more than by default 95% of the same values. And we use another option called fraction of embedding for sparse. It states for like the compression rate for this kind of columns. So for instance, if we have the this value equals to 0.2 and we have 10 sparse columns, the resulted number of columns will be equal to 2, because like 10 times 0.2. PCA is a technique with it's kind of lossy compression, which loses some data. However, the amount of data lost should be negligible. In general, for this example, we have some three-dimensional data, and if we look at this data at some other angle, we can see that this data may almostly almostly described by some plane. So we don't need 3-dimension. We only need 2-dimension. And on the most right plot, we can see this data on a 2-dimensional plane. And often the data can be described even by one-dimensional dimension if it lies on a single line. So this is also an effective way to reduce dimensionality. So one other thing for feature engineering is about cycling features. So cyclic features are kind of features which has the highest value is very close to the smallest value. For instance, for month day, the difference between 30th September and 1st October is 1 day, but effectively, if we use month day as is, the difference will be 30 minus 1 is 92, is quite large, which is not true. So to handle this, we generate two features from this one. Is about cosine and sine features. And as you can see, the difference between these features, like the derived features, is much less and is almost equal, like from 29th and 30th is almost the same as from 30th to the first one, as you can see on this middle table. And these values can be visualized like a circle on the right-hand side, and by the red ellipse, I try to highlight these particular dates. So moving on, the last thing is feature scaling. It's important for most algorithms which are based on continuous functions rather than trees, which are discrete in nature. So for continuous functions, for machine learning algorithms which are based on continuous functions, the features with larger values can have more weight into final model, which might be not true. So for instance, on the left table, we have that age is 10 times larger than male or female encoding, and income is thousands times larger than female and male encoding. And this way, the income feature will influence a lot on the final model, while this might be not so important feature. While after scaling, this data will be basically in the similar range. We scaled from 0 to 1, and despite the three models won't work worse on this data. They don't suffer from different magnitudes. However, we need to make the data in unified form, because as I mentioned previously, we optimize over different machine learning algorithms, and that's why we do this for all algorithms. And here I visualized the full pipeline process. This is quite a synthetic data set, and not all features are visualized, but I try to make it on a single slide. So imagine that our original data set is the data set from the first slide. Is this one on the right-hand side. So we have some several features. Say we consider only the first three. However, there might be much more features, and we want to predict income. So feature preprocessors are applied to features only, not to target for now. Here we have first we apply missing value. Sorry, I will tell some words about the colors. So the green color means that the feature is just appeared at this step. The red color means that feature will disappear on the next step, and the yellow color is both of the previous, like the feature has just appeared and will disappear in the next step. So at first, we have some data set, there is one missing value, and we impute it with the mean value over this column. And then we apply date and time preprocessor. So the last seen feature will be removed and replaced with some date and time features. So as we can see, like here appeared the month, day, weekday column, and so on. Next, we want to encode all categorical features, for instance, weekday or gender will disappear and are replaced with some other features related to category. And here, male and female appeared, as well as weekdays like Monday, Tuesday, and so on. As a next step, we want to apply feature elimination and imagine that some of features has low variance, or some of them are sparse, and we apply to all of features except age and month, day, the PCA first elimination preprocessor and then PCA preprocessor. And there are only two columns appeared, like PCA1 and PCA2, instead of all of these features. And this reduces our data size significantly. However, some information might have been lost. So next, we want to replace month-day feature as cyclic feature with the sine and cosine features, as I explained on previous slide. And then, as you can see, almost all features are in 0 to 1 range, while age has range from, say, 0 to like more than 100. And we scale, particularly we scale everything, but only age feature are effectively scaled. Other features remain untouched. And after that, we have the final data set, and we push it further to machine learning algorithms. One thing I want to know that this preprocessors works not only during the training time, but during prediction time as well. So when you try to serialize the model, like use it as a prediction service, it has not only a machine learning algorithm itself, but also all the stages of pipeline all stages of pipeline of data preprocessing included. So you will follow through this path during prediction as well. So one other thing about imbalanced data for classification, we handle this case as well using oversampling. We give a user three options, like random oversampler, adaptive, and smooth algorithm, and user can choose which one to use. Here is a visualization of this algorithm. On the left top is the original data, and all our sampling techniques are depicted respectively. So for random sampling, we just oversampled the class with the observations with the non-dominating classes. while two other approaches are quite difficult, and you can refer to imbalanced learn in order to get more details about these approaches. So thanks everyone for listening. I'm looking for questions from you.
Oh, yeah, sorry about that. I was just in the process of unmuting myself there, Vlad. Great presentation, really good information there. We've got a few questions that have come in. The first one here is there any theoretical basis for making it 50 maximum categorical columns, or is that an arbitrary number?
So actually, it's a more kind of arbitrary number. However, it's a kind of reasonable amount of columns. It mostly derived not from the data science perspective, however, but from like engineering perspective, like how much amount of columns our algorithm, our platform can use to train the data, and 50 is kind of reasonable amount, but usually it should be much less, and the feature elimination preprocessor will remove like the redundant features.
Okay, great. Next question. Do you search all permutations of the different preprocessing techniques, such as label versus one hot, PCA versus dropping features, that you could?
So actually, the order of preprocessors in pipeline are defined in this way in order to like make the final data set is mostly close to the goal I stated at the very beginning. If we permutate, for instance, the date and time preprocessor with the feature elimination, this might lead to redundant columns as well. So this kind of optimal order of preprocessors from my perspective.
Okay, great. Next question. Does Augur plan on supporting text preprocessing like tokenization, stemming, lemmatization?
Yes, it's our future plans too, because there are a lot of data which has like free text description, and it's reasonable to get some features from the description. And we also like can plan to add TF-IDF and some other features, maybe word-to-vec embeddings and so on.
Okay, sorry about that. Next question. Is the max number of missing values just the inverse of the max number of NAs, or is missing value different than NA?
Yeah, it's missing value, and NA is the same in this context.
Okay, great. I think we've got time for one last question here. I've noticed taking the log of a feature is a common preprocessing transformation. Does Augur do anything like this?
I'm sorry, can you please repeat the question?
Yes, I've noticed taking the log of a feature is a common preprocessing transformation. Does Augur do anything like this?
Okay, so currently Augur does not support custom features. That's because log is kind of manual feature extraction. Not this might either improve or spoil the results of final model. And currently we tried to we pursue the goal to make everything automatically. However, in future, we will add some custom features. This might be especially efficient for target feature transformation and especially for time series data. So this is our next goal.
Great. Well, I think that does it. That's all the time that we have for today. As mentioned earlier, a recording of the webinar will be made available via email. Thank you all for attending today's webcast. Vlad, thank you for sharing your expertise, knowledge, and time with us today. I hope everyone has a wonderful rest of the day. Bye-bye.
Thanks. Bye, everyone.